Friends, let us continue to discuss about the failure theories. In the last lecture, we discussed about two failure theories. We gradually started understanding and learning the importance of assessing the failure criteria. So, what we are trying to look here is to fix or to assess the failure criteria. Why is it necessary? I will explain this and interconnect this to the plastic design in the upcoming lectures. So, when the structural member is subjected to uniaxial, biaxial or triaxial stress states, different theories predict the failure stresses at different perspectives for unlike and alike stresses in a biaxial or a triaxial stress states. So, in this context, we discussed about two theories in the last lecture. Now, we will talk about the third theory in this lecture, which is the maximum strain theory. This theory is also known as Saint-Venant's theory. The statement of the theory is like this: in a given complex stress state, yielding at any section, we will also say this as critical section, begins in a material when the maximum strain exceeds the strain corresponding to the yield point of the material. So, this theory focuses essentially on the strain criteria. That is why it is called maximum strain theory. If sigma 1 and sigma 2 are the principal stresses under the condition that sigma 1 is larger than sigma 2 in magnitude. Strain in the direction of sigma 1 is given by the following equation: epsilon 1 is sigma 1 by E minus mu times of sigma 2 by E, and of course, this cannot be greater than the corresponding strain at the yield point. We will call this equation number 1, or sigma 1 minus mu sigma 2, worst by worst can be equal to sigma yp. That is what the theory states. Now, if both the stresses sigma 1 and sigma 2 are of same nature, let us say maybe tensile, then substituting this condition in equation 2, we get sigma 2 minus mu sigma 2 is sigma yp, which means that sigma 1 will be sigma yp plus mu sigma 2, which exceeds even sigma yp, is it not? So, that is a very interesting condition. Of course, this condition does not occur when sigma 1 and sigma 2 are dissimilar in nature. For sigma 1 tensile and sigma 2 compressive, equation 2 will become sigma 1 minus mu of minus sigma 2 as sigma yp, which says that sigma 1 will be sigma yp minus mu sigma 2. So, in this case sigma 1 does not exceed sigma yp, is it not? But whereas in the earlier case, if both stresses are same in nature, let us say both are tensile, there is a probability that one of the principal stresses can even exceed the stress at the yield point. So, this is an alarming condition which says that when both the stresses are tensile, there exists the possibility of sigma 1 greater than the stress at yield point. That is, sigma 1 even exceeds sigma yp, even without causing yielding in the material. That is very interesting. So, one can then say that the maximum strain theory is an improvement upon the principal stress theory. This theory, as observed in the literature, this theory does not hold good for ductile materials. It is better for brittle materials. So, let us try to plot this theory graphically. So, you must understand one important statement: for sigma 1 and sigma 2 both being tensile, sigma 1 can even go higher than sigma yp. Same story for sigma 1, sigma 2 both being compressive. Still sigma 1 can exceed sigma yp. It means in the first and third quadrants, sigma 1 exceeds sigma yp. I should say plus or minus sigma yp. Okay? Let us say the x axis plots sigma 1 and y axis plots sigma 2. This is positive and this is negative sigma 1 and this is negative sigma 2. Okay? So, let us try to get a control line to plot this failure envelope, which you used to do for the remaining theories as well. Let us say my sigma yp is here. These are my sigma yp's. Okay? So, ideally speaking, this value should be sigma yp, but for sigma 1 and sigma 2 both being tensile, that is the first quadrant, I am getting sigma 1 more than sigma yp. So, let us take that point as somewhere here. Similarly, even in the third quadrant, for sigma 1 and sigma 2 both remaining compressive, even this is true, it exceeds. Whereas, in the off diagonal sides, these values are lesser. I will come to that point how we work it out. So, the envelope says it should cross sigma yp and on the dissimilar states, so let us try to write down these equations for this particular state line. So, in this case it will be sigma 2 minus mu sigma 1, which will be yp. So, sigma 2 exceeds sigma yp. This particular line, the equation will be sigma 1 minus mu sigma 2 will be sigma yp. So, sigma 1 will exceed sigma yp. Similarly, this particular line sigma 2 minus mu sigma 1 will be minus sigma yp. This particular line, it will be sigma 1 minus mu sigma 2 will be minus sigma yp. Let us talk about this particular line. Let us say we will divide this line as A, B, C, D, E, F, G and H. So, this equation is for AH, this equation is for AB, this equation is for EF, this equation is for ED. Let us write down the equation for CD. You know, here it is dissimilar state. Sigma 1 is tensile compressive, sigma 2 is tensile. So, it should be sigma 1 plus mu sigma 2 will be minus sigma yp. This is for CD, whereas GF will have sigma 2 plus mu sigma 1 as minus sigma yp. Now, let us come to the line, this is for GF. Let us come to the line equation BC. So, this equation will be sigma 2 plus mu sigma 1 will be sigma yp. Okay? This is for line BC, and this line will have an equation sigma 1 plus mu sigma 2 will be sigma yp. This is for the line GH. So, this is my failure envelope. As we understand, any point lying on the periphery or inside or outside. So, if I say A, B and C, A indicates failure, B also indicates failure, C no failure. So, we can write a very interesting information here. In the second and fourth quadrants, that is the value at C and G are lesser than sigma yp. It means when the stresses are dissimilar in nature, the prediction of failure is poor, because it says the system fails even before yielding, isn't it? Because this value is not sigma yp, sigma yp is somewhere here, it is somewhere here, but it fails at G, which is much lower than sigma yp. Whereas in quadrants 1 and 4, when both stresses are either tensile or compressive, that is similar in nature, it says one of the stress even exceeds sigma yp. Then only the failure will occur. Okay? Without yielding, failure starts. Whereas, when sigma yp is reached, yielding should initiate in the material. So, one can see very well here that this theory has a lot of controversies. In a biaxial stress state, when the principal stresses are same in nature or different in nature, that is represented in all the 4 quadrants as you see in the figure on the screen. I think it is very easy and convenient for all of you to really know how do we generate these equations. For example, take this equation. This is same equation as equation 2, whereas sigma 1 being positive, sigma 2 will exceed sigma yp, is it not? So, this line, for example, I am marking in black dotted, this line is the rate of growth of sigma 2, the rate of growth of sigma 2 beyond sigma yp has an influence from sigma 1. So, that is how this equation is written. Similarly, if you want to find the rate of growth of sigma 1 beyond sigma yp as an influence from sigma 2, this equation is written. So, by this algorithm you should be able to realize the equations of all other segments in various coordinates and various quadrants represented as shown on the screen. So, let us move on to the next theory, which is total strain energy theory. So, now we are looking at the fourth theory, which is total strain energy theory. This theory was proposed by Haig. It is also called as Haig's theory in the literature. The statement of the theory is as follows: inelastic action or yielding at a section begins only when energy per unit volume absorbed at a point So, energy absorption is actually the strain energy, okay, is equal to the energy under uniaxial tensile test or uniaxial stress state of the material, which is obtained from the simple tension test . This theory has got a very interesting and major contradiction. This theory says, in this case, failure does not depend on the stress state. That is a very interesting deviation this theory gives in comparison to the remaining three theories. But failure is governed by the energy stored in the material. Per unit volume. So, the focus is on strain energy. Okay. Let us get more details of this theory and derive the controlling equation for the failure envelope. Let us assume a triaxial stress state. Where the following condition is satisfied. The condition is sigma 1 exceeds sigma 2 exceeds sigma 3. For this state, epsilon 1, epsilon 2 and epsilon 3 are given by the following equations. It is very easy. Please look at the screen carefully and then watch how I am writing this equation. When you talk about strain, it is stress by Young's modulus. So, sigma 1 minus Poisson's effect on the remaining two axes. So, when you talk about epsilon 2, it is sigma 2 minus Poisson's effect on the remaining two axes. When you write, please see the order 1, 2 and 3, 2, 3 and 1. So, I think you have to follow this order. So, by this logic, now we can easily write epsilon 3, which is sigma 3 minus mu of 1 plus 2. Okay. I call this equation as 1a. Once I know the strain values, I can always find the strain energy per unit volume. Which is usually expressed as U, which is given as half sigma 1 epsilon 1 plus half sigma 2 epsilon 2 plus half sigma 3 epsilon 3. I call this equation as 2. Now, I have the equation for the strains along 3 principal axes 1, 2 and 3, which is given by equation 1a. Let us substitute 1a in equation 2 and see what happens. So, substituting 1a in equation 2, we get the total strain energy per unit volume U, let us say 1 by 2E, okay, because you see 1 by 2 is here and E is here. So, 1 by 2E sigma 1 times of epsilon 1, which is sigma 1 minus mu of sigma 2 plus sigma 3. Plus sigma 2 times of sigma 2 minus mu times of 3 plus 1 plus sigma 3 times of sigma 3 minus mu times of 1 plus 2. Okay? I think it is very easy to substitute, you can do it yourself. Let us simplify this. So, 1 by 2 E of, one can see here this product will give me squares. So, let us say sigma 1 square, sigma 2 square, sigma 3 square. Then you will also see sigma 1 sigma 2 once and sigma 1 sigma 2 twice. So, you get 2 products of both repeatedly. Okay? Let us do that. Minus mu times of sigma 1 sigma 2 plus sigma 1 sigma 3 plus, let us say, sigma 2 sigma 3 plus sigma 2 sigma 1 plus sigma 3 sigma 1 plus sigma 3 sigma 2. Okay. Let us put it in green. Okay. Now, you see 1 sigma 2 here, 1 is here. Similarly, sigma 1 sigma 3, sigma 1 sigma 3. Similarly, sigma 2, sigma 3 and sigma 2, sigma. So, there are two values here. So, therefore, let us simplify this further and say it is going to be 1 by 2 E of sigma 1 square, 2 square, 3 square minus 2 mu of sigma 1, sigma 2, 2, 3 and 3, 1. Agreed? We will call this as equation number 3. Okay, I hope there is no confusion in this derivation. Please follow, it is very interesting and very important, and I want you to derive as I do it on the screen, so that you have no confusion later and you do not have to memorize anything. Okay, learning is a very important skill, friends. We are emphasizing on learning, not on memorizing. Once you learn, keep on doing it, you will understand. Once you understand, there is no question of memorizing it, there is no requirement for that. Okay. So, let us focus on that very clearly. So, equation 3 gives me the total strain energy per unit volume of the material. Now, if the stress state is biaxial, that is sigma 3 is 0, then let us see what happens. Then equation 3 will become u equals 1 by 2 E of sigma 1 square 2 square minus 2 mu of sigma 1 sigma 2. Is it not? It is very obvious. Let us call this equation number 4. And more simple, for an uniaxial stress state, put sigma 2 and sigma 3 both as 0, then we get u is going to be sigma 1 square by 2 E. Now, the theory says this is where the yield value will be reached, is it not? Hence, I can say strain energy at yield point will be similarly the stress at that point divided by 2. Can I say this? Equation number 5. I think we all agree to land up in equation 5 without any confusion. So, equation 3 is for triaxial stress state. Okay. Equation 4 is for biaxial stress state. The theory says equation 3 or equation 4 should be identical to equation 1, is it not? That is what the theory says. Please read the theory, or not equation 1, equation 5, sorry. So, let us equate that. So, for a triaxial stress state, should be equal to sigma yp square, am I right? For a biaxial stress state, we call this equation number 6 and this equation number 7. Take a simple case. Please look at equation 7. Equation 7 actually represents an ellipse. With the condition that the major and minor axis of the ellipse are placed at 45 degrees to each other. Look at this factor. Okay. So, let us plot this envelope. Let us call this as sigma 1 and this as sigma 2. Let us say this is positive axis. Let us draw the major and minor axis of the ellipse at 45 degrees. Okay. Now, in this equation, if any one stress value is 0, in equation 7, if any one is 0, you will automatically see the corresponding axis will be representing the sigma yp. So, sigma yp should be marked and the curve should pass through sigma yp. Let us mark. So, these are all sigma yp's. Okay. So, let us draw the ellipse. That it cannot cross sigma yp. So, when you draw this ellipse, let us be very careful about this. So, I have drawn the ellipse. Okay. This angle is 45 degrees. Now, let us do some calculations for sigma 2 equals 0. We know sigma 1 is plus or minus sigma yp, which is indicated here. For sigma 1 equals 0, sigma 2 will be plus or minus sigma yp, which is indicated here. So, let us to pass through these 4 points which is passing through. Okay, the curve has to pass through this point. Let us say we will draw the curve passing through this point. Okay, let us, okay. Right. For sigma 1 equals sigma 2 equals sigma, that is the stresses are same magnitude. Then in that case, sigma will become plus or minus sigma yp by root of 2 1 minus mu. Please do this calculation and check. Same intensity, okay, same magnitude, this equation is true. For a typical value of mu as 1 by 3, you will find the stress will become plus or minus 0.87 sigma yp. So, this value, when the stress of the same intensity and nature may be tensile, may be compressive, this is 0.87 sigma yp. It is not sigma yp, please understand that. So, the curve should not pass through this point. Okay. Further, for sigma 1 equals sigma and sigma 2 equals minus sigma, that is we are talking about now the second and the fourth quadrant. In that case, you will see sigma will be plus or minus sigma yp by root of twice 1 plus mu. Please see this equation, which gives me for mu equals 1 by 3, this stress value will become 0.613 sigma yp. So, these values are 0.613 sigma yp, correct. So, this is my failure region, safe region, and anything exceeding this is a failure region. So, this theory predicts that at failure yield stress is not reached, is it not? It is only about 87% the material fails or the failure happens in the member, even though the material has not touched the yield stress, when the stresses are similar in nature and same magnitude. When they are dissimilar in nature, failure occurs even much lower than sigma yp. So, that is a very critical and dangerous composition and interpretation this theory gives me. Okay. So, friends, let us quickly see the summary what we learnt in this lecture. The summary says we have learned two more additional theories. We have also saw that these theories show good disagreement when the stresses are dissimilar in nature. One of the theories says when the stresses are tensile or compressive, both of them, that is in first or third quadrant, the stress even exceeds sigma yp without yielding, which is not correct, because when the stress exceeds reaches sigma yp, yield has to start in the material, is it not? So, this theory, one of the theories amongst these two, I leave it to you which theory is that which gives you this. And the failure envelope is elliptical or a rhombus, depending upon the pattern what you assume. So, it is very interesting and critical to really guess what theory will be used for assessing the failure condition, because at failure condition the engineer desires to know what is the stress. It is not always that when the stress reaches sigma yp, failure starts. The theory says even at 0.87 the failure can happen, even at 0.613 the failure can happen, and so on. So, there are serious discrepancies suggested by these theories when we talk about failure, is it not? Thank you very much. Have a good day.